Hello everyone, welcome to today's lecture on laser. Here we will study the fundamentals of laser, the basic physics of laser, the operational principle and its application. As a particular case, we will study in detail about helium neon lasers, that is HENE lasers. Okay, so without further ado, let us start. So, laser fundamentals. Here we will try to understand laser principles and their basic applications. We'll start with the basic physics behind laser and lasing action. To begin with, we'll discuss the full form, that is the meaning of the word laser. It stands for light amplification by stimulated emission of radiation. A laser produces highly intense, coherent, monochromatic and directional beam of light. Unlike ordinary light sources such as bulbs or LEDs, laser light has very special properties that make it extremely useful in science, engineering, medicine and communication technology. The fundamental principle lies in its quantum mechanical foundations. It is based on the atomic and molecular interactions governed by quantum mechanics and stimulated emission. Now, the operation of a laser is based on the principles of quantum mechanics and atomic energy transition, as we already mentioned. In a laser medium, atoms absorbs energy and move to higher energy states. Under suitable conditions, these excited atoms release photons through stimulated emission, leading to amplification of light. So, some of the basic principles of laser is first obviously the stimulated emission, then population inversion, its optical feedback and coherent laser beam. We will discuss about population inversion detail later on. Now let us focus on the basic characteristics of laser. The first property is its monochromicity. Laser light consists of a very narrow range of wavelengths. In ideal case, it is considered to be a single wavelength light source. However, practically there is always a small spread in wavelength or frequency due to the effects such as Doppler broadening, natural broadening and collision broadening. The second property is coherence. Coherence means maintaining a fixed phase relationship between the light waves. This we already have discussed in interference chapter. Okay. Laser light is highly coherent because the emitted photons have the same frequency and phase relationship. Coherence may be temporal, that is related to time, or it may be spatial, which is related to space. Another very important property is its directionality. Laser beams are highly collimated and spread very little, even over large distances. So this makes laser useful in long distance communication and precision alignment systems. Laser beams also possess very high intensity because the energy is concentrated within a very small cross-sectional area. To understand laser action, we must first understand three fundamental atomic processes. Its absorption, spontaneous emission and stimulated emission. Okay. In absorption process, an atom absorbs a photon whose energy matches the difference between two energy levels, two atomic energy levels. Here we have E1 and E2. E2 is greater than E1 here. So, as a result, the atom moves from a lower energy state to a higher energy state. Absorption plays a very important role during pumping in laser systems. Next comes spontaneous emission. In spontaneous emission, excited atoms return to lower energy states naturally, and by this they emit photons randomly in different directions and phases. Ordinary light sources such as lamps, they mainly operate through spontaneous emission. Since the emitted photons are random, ordinary light is incoherent. The most important process for laser operation is stimulated emission. In this process, an incoming photon interacts with an excited atom and stimulates it to emit another photon. The emitted photon has the same frequency, phase, direction and polarization as the incident photon. Therefore, stimulated emission produces coherent and monochromatic light. This process also creates photon multiplication, leading to amplification of light inside the laser cavity. Now, for stimulated emission to dominate, we require a special condition known as the population inversion. Normally, most atoms remain in ground state. In population inversion, the number of atoms in the excited states become greater than the number of atoms in the lower energy state. This non-equilibrium condition is essential for laser action. To achieve population inversion, different pumping methods are used. These include optical pumping, electrical pumping, inelastic collision pumping, chemical pumping and thermal pumping. In optical pumping, intense light excites the atom. In electrical pumping, energetic electrons excite gas atoms through collisions. Inelastic collision pumping is used in HENE lasers, where excited helium atoms transfer energy to neon atoms. An important concept related to population inversion is the metastable state. A metastable state is an excited state with a relatively long lifetime compared to ordinary excited states. Since atoms remain in this state for a longer duration, population inversion becomes easier to achieve here. Most laser systems are designed in such a way that atoms accumulate in metastable states. Now, let us discuss the helium neon laser in detail. The HENE laser, it is a gas laser that uses a mixture of helium and neon gases as the active medium. It is one of the earliest continuous wave laser and is widely used in laboratories and optical experiments. The laser commonly emits red light of wavelength 632.8 nanometers. The construction of HENE laser consists of a long glass discharge tube filled with helium and neon gases in a suitable ratio. Electrodes are connected at both ends of the tube to produce electrical discharge. Two mirrors are placed at the ends of the tube forming an optical resonator. One mirror is fully reflecting while the other is partially reflecting, allowing a small fraction of laser beam to emerge as output. Brewster windows are also used to minimize reflection losses and produce plain polarized light. Now, let us understand the working principle of HENE laser. When high voltage is applied across the discharge tube, energetic electrons collide with helium atoms and excite them to higher energy metastable energy states. These excited helium atoms then collide with neon atoms. Since the energy levels of excited helium and neon atoms are very close, energy transfer occurs efficiently through inelastic collisions. As a result, neon atoms are excited to metastable states. This process creates population inversion in neon atoms. The excited neon atoms then undergo stimulated emission and they emit photons of wavelength which is around 632.8 nanometers. These photons travel back and forth between the two mirrors inside the optical resonator. Continuous amplification occurs through the repeated stimulated emission, and finally a coherent red laser beam emerges through the partially reflecting mirror. The HENE laser has several advantages. It produces highly stable and monochromatic coherent directional light. Due to these properties, it is widely used in holography, interferometry, barcode scanners, alignment system, in spectroscopy and in educational laboratories. Now finally, let us briefly discuss some of the general applications of lasers. Lasers are used in medical surgery, in therapeutics, optical fiber communications, industrial cutting and welding, in scientific measurements, holography, range finding and defense technologies. Because of their precision and high intensity, lasers have become essential tools in modern science and technology. With this, we conclude today's lecture on fundamentals of laser. I would be happy to take some questions from your side.